Hi, my name's Ed Holloway. I'm a PhD candidate with the Sustainable Minerals Institute at the University of Queensland. My research has been focusing on risk and strategy in mineral asset optimisation and valuation. Today I'm going to talk through a subset of that research, focusing primarily on the way that risk impacts into valuation. So to cover that, I'm going to look at how we make strategic decisions and how that can be significant. I'm going to talk a little bit about the relationships between value, risk and strategy and how that ties into one of the main research gaps that I've been focusing on. I'll provide a little bit of context around the research and a key part of the hypothesis, and then I'll provide an example of how some of the issues or the research gaps can manifest in terms of the way that we perceive value, particularly in a strategic context, and then I'll close out from there. So to start with, how do we make strategic decisions? A lot of the time strategic decisions are based around value and will solve to an objective function. Now risk impacts on value, that's fairly well recognised, and we'll often use a standard discount rate that's constant across different strategic scenarios to incorporate risk. So this slide isn't intending to say that non-value based metrics are not significant. They absolutely are, but they're generally bespoke to that operation, whereas the value concept is applied almost ubiquitously across valuations. So the combination of those means that pretty much every single discipline will be impacted in the way that their work is wrapped up into this broader strategic perspective. So how's that significant? Think of the sizing of the ultimate pit. There's a component of risk involved in that, which if we use a standard discount rate we largely ignore. That directly impacts the size of waste management facilities, so waste dumps, tailing storage facilities, etc. The way that we consider risk also has a significant impact on how we might consider the adoption of any new technology. And it also impacts on the way that we apply basic policies such as cut-off grades. So to provide a little example of that, if you have a very large closure cost, if we optimize according to standard theory, you would actually run the business at a loss and process waste just to delay that closure cost. Most people don't do that, but that's a sort of thing, type of issue that can arise in the standard structure of the way we view things. Okay, so what's the relationship between value, risk and strategy in the status quo? Risk impacts value. We know that the higher the risk, the greater the value you'd want to see to invest in that risky investment. And we know that strategy impacts on value. We also know that strategy impacts on risk. So a lot of the strategies that we'll devise are focused on risk reduction. And that bottom orange line is coloured orange because there's an issue there. We use the same discount rate regardless of the strategy. So in fact we're ignoring that bottom line. And that is a big part of the research gap. So what the discount rate's attempting to do is combine time and risk into the one factor. So if you need to disaggregate that, then there's actually not a mechanism or a framework by which to do this that's not going to invalidate all of your prior optimization work. So I've coined this as being the objective function problem. What is the objective function problem? What do I mean by that? What I'm driving at there is that if we choose to consider risk, say in the financial model, and then we've actually changed the objective function, and so that any work that was done prior, any pit optimization or schedule optimization that was solved to that prior objective function, once we've changed it, it's been invalidated to an extent. So then to correctly apply risk, we're going to need to apply it at source or as close to the source as possible. So a little bit of context what I'm talking about there. I'm talking about risk in a bidirectional context, not downside risk only, so more pure risk, and I'm focusing on individual mining assets. So that's important because it's different to portfolios, because portfolios have an amount of diversification which changes that risk profile. I'm talking about active strategy, so for people that are actually trying to improve what they're doing, not someone that just wants to expect that they'll get a certain return. And we're looking at strategic level decisions as distinct from tactical. So a high level illustration of what I'm talking about there is if we've got that corporate portfolio at the top there's an amount of diversification in it. There's 14 assets in there, and as one's having certain problem, another one won't be. And a small amount of diversification in fact does an awful lot to reduce risk. What I'm talking about is how do we quantify the risk that's impacting on, say, asset 10, and how does that then impact on the way we make strategic decisions? To apply those risks at source, I've gone back and looked at just a generic planning framework. So this one here has a series of data coming in terms of geological and metallurgical data at the top, cascading through to a financial model, a corporate financial model down on the bottom left. Now, I've, in this slide, highlighted the two key areas that need to be focused on for that, which is pit optimization and schedule optimization. So a great deal of the focus on how to apply risk has been in those two areas. With that bit of context, I'll provide the basic research hypothesis for my research, which is that the disaggregation of time and risk will provide a more accurate representation of project risk, and this will change the valuation and the strategy. Okay, so risk and valuation. This is an example, it's a subset of the research, and I'll just take a quick run through this to illustrate how different ways of considering risk can materially impact on value and then also on strategy. So as far as the literature goes, the literature is enormous. It impacts on multiple industries, and there's common issues. So if we have a quick look at a timeline here, lots of contributors going all the way back to Marx and no doubt before that, and plenty of work still ongoing in this space. We've absolutely not solved all of the problems. What's the summary of that? Time and risk are not the same. They're logically separate variables. Risk is not constant. Time is. Standard discounting is mathematically incorrect. Portfolio risk differs as compared to individual project risk, and greater detail and scenario analysis is going to be required if we want to solve any of these problems or materially improve on the outcomes. We can also state that corrections to risk modelling will result in changes to the outcomes and the subsequent decisions we would make. In a mining context, what does that mean? It means that NPV with standard discounting has conditional validity. We can expect it to be accurate in instances where we're considering portfolios as opposed to single assets. Shorter life assets will be accurate. Longer life assets will have a constant directional error in it. If we have varying risk profiles, standard discounting does not work well. And if we have varying strategic options, standard discounting also does not work well. Standard discounting also doesn't deal well with large upfront capital or any long duration cost profiles. So think of rehabilitation as an obvious one there. So what's the gap there? Risk cannot be adequately incorporated into a valuation using a single factor. Standard discount rates do not work well. Risk and time must be disaggregated. The second point here is that impact of the discount rate is compounded through time. That's critically important, but it's not been a focus of my research to date. So the aims and the objectives of this piece of the research is to compare the valuation results using standard discounting and at-source discounting, and then assess whether or not it has any impact on types of strategic decisions that we would make. Okay, so I'll have an illustration here. It's a greenfield project, it's a big one, and we're going to consider how we should invest in it. So it's a copper porphyry, 1.4 billion tonnes, and we're going to consider a range of throughput scenarios from 6 million tonnes through to 90 million tonnes. And we've got a range of construction timeframes and capital costs. They're all fairly well matching the size of the construction that would need to be implemented. So if we apply a standard NPV, this is sort of profile that we get. It looks very common for that type of big deposit. It goes up and flattens off. NPV structurally drives that type of curve because it has, as the capital increases, the capital intensity actually decreases. So if you think about that, you only need one airport. You only need one road. Your footings, you won't need to duplicate every footing. You'll be able to incrementally expand on it. And this is illustrated in this graph here, where you can see the orange bar is showing that the capital intensity is dropping as the scale and the capital increases through the blue bar. And this is part of what's driving that curve. But what's missing from this is risk. If we use a standard risk, we're assuming that the risk is by and large constant. But it's not. Here's some data that this is largely extracted from McKenzie and Cusworth, who've done some really interesting work in this space. And if you extract their data, and I've modified it so that it's all in US dollars, there seems to be a fairly clear trend that risk does increase with scale in terms of both cost and schedule overruns. And this is this aligns with the work from Flyberg, who's analysed quite a lot of work, non-mining work, but it also correlates with these results. If we just pull out a linear relationship, it becomes even clearer. Cost and schedule overruns increase as the scale of the project does. Now, I've modeled this stochastically, and I've used a negative binomial distribution. And in a 10-minute talk, we don't have time to cover why. But if we do that, we get this type of a result. And we can see here that immediately, so we've got on the x-axis the throughput, and on the y-axis the resulting NPV. We can see immediately that the risk or the probable range of outcomes for the larger cases has increased significantly compared to the smaller cases. If we look at this as a box of whisker, we can now start to see that the 90 million tonne case is clearly, if the line on the box of whisker is the average, we can see that it's too big. A slightly zoomed axis here, sorry, again, the throughput on the x-axis and the NPV on the y-axis, we can see that the 90 million tonne case is clearly too big, as is the 60. You could argue very well that the 24 million tonne case would be a good place to start, because you've got a lot less risk, you've got better confidence, you've got shorter time frames. It's a very different looking profile because we've considered risk at source. If we now compare this using the standard discount rating to the at source discount, you can see that the blue line is the 12% discount rate, and then we've got the grey line as the 5% discount rate. The at source risk adjustment is the orange line, so that's where the risk has been applied based on the stochastic inputs. And you can see there that it actually drops down below the 12% line, implying that at a 90 million tonne case, 12% is actually too low. But it's not temporally diversified either, whereas the at source risk quantification is. So now we've got a very clear case to select a throughput that more matches what people might be comfortable with. People intuitively feel that the 90 million tonne case is likely too big. Generally, people will be quite uncomfortable with such a large project. So conclusions from that. A constant discount rate masks changes in risk. An at-source risk quantification of risk changes the valuation of risk and therefore of the asset. As a result of that, any strategic decisions can be expected to be impacted. To close out, risk impacts value, strategy impacts risk, and standard discounting obfuscates strategy. Thanks.